Welcome to week 2 of Climate Match Academy. In today's tutorials, we'll be talking about future climate, the physical basis. But before we do that, I just wanted to give you a bit of background about myself. I know we met at the end of last week's climate modelling day, but I'm Brody Pearson, for those of you that don't remember, and I'm an assistant professor at Oregon State University in the USA. I got my degrees in the UK, then I moved to the USA for a postdoc where I've been ever since. My research interests are in using and developing numerical models for the ocean and climate systems. And specifically, I'm a physical oceanographer. I look at turbulence and other processes that mix properties within the ocean. And I develop parameterizations for those processes, which is something that we'll talk about a little more later today. So now let's dive into tutorial 1, where we'll be recapping Earth system models, which we encountered at the end of our climate modeling day last week. So you worked a lot with climate models in general on week 1, day 5, and you found that these models can take an initial climate state and use physical rules to estimate what the climate may look like at a later time. And by repeating this for many time steps, these climate models can project far into the future. And for that reason, climate models, and specifically Earth system models, which are our most complex and realistic climate model, provide us a window into the future that we can't get from things like observations. And so we're going to be focusing very heavily on these system models and how we use data from them in today's tutorials. So for this reason, we'll do a quick recap of the 3 ingredients that we talked about in the climate modeling day of an Earth system model. We have to discretize an Earth system model. We have to choose time steps and grid cells. We have to chop the planet up into these spatial boxes that properties can get moved between in the ocean, atmosphere, land and ice systems. We have to define a set of physical relations that we want the model to use to predict how air, water, heat and other properties get moved between grid cells. And we have to convert those physical relations into algorithms that a computer can interpret and evolve. And all these ingredients can differ amongst different Earth system models, and we'll be talking about that a lot today. But in this first tutorial, you're going to be taking data from an Earth system model and plotting maps of that data and how data changes over time. And for that reason, for this tutorial, it's worth talking a little bit about discretization, because if you're going to plot maps, you want to know where your grid cells are, and so where you should be plotting each piece of data. So you've already encountered methods to plot mapped data, spatially discretized data, earlier in week 1, where you worked with observations that are on a regular latitude-longitude grid. And so many Earth system models do use a latitude-longitude grid. Maybe it has 1 degree grid boxes, maybe it has half a degree grid boxes, or different size grid boxes. So the size of these grid cells can vary between Earth system models. They don't all have the same set of grid cells. But Earth system models can also be a little trickier because they don't necessarily use regular latitude-longitude grids. So some have more poles that are in different places than Earth's real poles for computational reasons. Others might focus their resolution in certain places where there are important physical processes that need to be resolved. In fact, when you get to some of the most cutting-edge models, not all of them even use rectangles. Some use triangles, hexagons, and more complicated polar structures, like this soccer ball here, for example. Shows that you can construct a sphere out of something that is not necessarily squares. In this case, it's a mixture of hexagons and pentagons. And so grid cells and gridding of model data can get pretty complex and differ between different Earth system models. And so you're also, in this tutorial, as well as plotting data from spatial data from an Earth system model, you're also going to regrid that data to put it on a specific grid that you specify. And this is a really useful and important capability to have, because if you want to compare model data from different models that are on different grids, or perhaps compare this model data with observations that could also be on a different grid, then you need to convert them all to the same grid in order to do a comparison, like a spatial difference. How does the temperature at a certain location, for example, differ between these models or models and observations? And so that's what you're going to be doing in this first tutorial, is taking spatial data sets from an Earth system model, plotting those data sets, and then regridding them onto a grid that you will define.